Is that okay?
Yes.
Okay, thank you. Good. All right, so it's very nice to be with you all in Boulder, even if only virtually, I'm sorry. I think it's a very exciting school and it's nice to have the chance to be part of it. So I've been asked to give 3 lectures in this school that overall is about hydrodynamics on the topic of complex fluids. So I've given a deliberately hydrodynamic type of focus to that. So the outline of my slides my talks is as follows. So I'm going to start by introducing complex fluids in general, and in particular introducing the topic of rheology, that being the study of the deformation and flow properties of materials and complex fluids and soft materials. So I'll give an overview of those, and then I'll introduce the approach to modeling them at a continuum level. And then what I'll do is essentially a study in the kind of flow instabilities that I'm sure you'll have by now encountered in many other hydrodynamic systems by doing what we often do in studying instabilities, which is working up through the spatial dimensions from initially being homogeneous to allowing spatial variations in increasing number of dimensions. So I'm going to do that first of all in the context of passive complex fluids. I'll then more briefly and by more or less by direct analogy, talk a little bit about the hydrodynamics of active fluids, but I'll do that. I know that you've already had some lectures on active fluids, and I'll do that essentially to draw a deliberate analogy with the rheology of complex fluids. So although you have seen active fluids up to now, I think you won't have seen them discussed in quite the way that I'm going to do here with this more rheological focus. And again, by analogy, I'll start with an overview, present some continuum models, and then essentially do a study in bulk flow instabilities. Obviously, an important part of doing research is doing, in many cases for theoreticians at least, is doing numerical simulation. And so aware that not all of you will have a background in that, and part of the function of a summer school is to learn practical tools as well as the background theory. I'll then give a pedagogical introduction to the kind of numerical methods that we use in the group to study these continuum models and the instabilities that arise within them. So in the whole of this first part of the lectures, A and B, will be focusing on instabilities that occur within the fluid bulk. In what will probably be the final lecture, but we'll have to see a little bit how the time goes, and this is deliberately modularized to allow plus or minus according to how quickly we go and how many questions we get. But I'll talk about instabilities then that arise at the surface where a flowing complex fluid meets the outside air, for example, or where it meets the hard walls of the flow cell. Okay, so those are the plans of the lectures as a whole. It remains to be seen, as I say, depending a little bit on the time, how neatly these fall into 3 lectures as such, but we'll see how we get on. I think today we'll get at least as far as here, and we may even get into this second topic. All right, so the rheology of complex fluids then. So as I said, I'm going to start with an overview of complex fluids. I'll then talk a little bit about the approach to modeling them, and I'm going to do so at a continuum level in these lectures. Obviously, there are a lot of people who also model complex fluids using what you might call particle-based simulations, molecular simulations too. But here I'll be focusing on the kind of continuum models that seem more suited to a school on hydrodynamics. And I'll then talk about rheology, that is deformation and flow, and talk about the kind of bulk instabilities that occur when you start solving these continuum models in increasing spatial dimensions. All right, so let's introduce complex fluids then. So what do we mean by complex fluids? Well, there are many different examples of these, classes of these. These include surfactants, liquid crystals, polymers, foams, emulsions, colloids. And they find a huge range of applications, both in nature and technology. So, for example, the membranes of biological cells inside our bodies are essentially made of surfactant-like molecules. Liquid crystals, like materials, are found in cartilage and viruses, but they're also used technologically in displays. Polymers obviously find very wide applications in plastics, but actually also the basic molecule of inheritance, DNA, is a polymer. Foams and emulsions used in foods, firefightings, pharmaceuticals, and so on. Now, the unifying feature that is common to all of these complex fluids and that distinguishes them from a simple, well, a supposedly simple fluid such as water, although I'm sure those who study water would not say it's a simple liquid. But the unifying feature that distinguishes these complex fluids from what we might think of as a simple fluid such as water is that they have inside themselves internal substructures that are mesoscopic in size. So by that, I guess I mean on the scale of typically nanometers to microns, although maybe even millimeters in the case of foam bubbles, for example. So, for example, we might have long rod-like molecules in a liquid crystal, long chain-like molecules in a polymer, fractal aggregates in a colloid, bubbles or droplets in an emulsion. Now, the presence of these internal substructures then confers on these complex fluids, sometimes also, by the way, called soft materials, and those words, descriptions are often used interchangeably. These materials are soft, most notably under an applied shear. And the reason for that is that the typical energy scale for deforming an initially undeformed, unsheared configuration of these substructures, the energy scale for that is typically entropic, so in other words, set by kT, as compared to the strong bonds that hold together a conventional hard, solid, crystalline solid, such as a salt crystal, for example. So these materials are soft under an applied shear. There are other properties that arise from the fact that they have these internal mesostructures, such as viscoelasticity. They're easily driven into nonlinear flow states. They show non-zero so-called normal stress differences, and they display so-called flow-induced transitions. So I'm going to go then through each of these next 4 properties on the next 4 slides in turn. So first of all, viscoelasticity. So this is a concept that crops up almost ubiquitously in the discussion on in any study of complex fluids. So what do we mean by this? So if we take a slab of complex fluid and sandwich it between 2 plates, and then we suddenly deform it by moving here the top plate slightly to the right compared to the bottom plate, and that defines a shear strain. That is defined, in fact, as the amount by which we move the top plate normalized by the gap size. So it's effectively a measure of the change in shape of the material, or this characterizes this angle here. And here we're interested in the so-called linear regime where this is small. So in other words, for all times before time 0, the strain has been 0, and this was just a rectangular block. And then at time 0, we apply a strain and it becomes the shape of this parallelogram here. It's been sheared. And as a result of this deformation, we expect some shear stress. This is force per unit area to be generated. And we then expect that to decay away as a function of the subsequent time, t. And we characterize that decay by some timescale tau, the typical timescale on which the stress falls to, say, half of its original value. So what is that timescale tau? How big is it? Well, so here's a line of values of that relaxation time. So we're all used to conventional so-called simple liquids, such as water, supposedly simple, in which that relaxation time is tiny. And the reason for that is that as soon as we apply shear to a simple liquid, the molecules which are rapidly jostling about under Brownian motion almost immediately rearrange and to accommodate the applied shear. And so the stress decays almost instantaneously. At the other limit, we're also used to conventional elastic solids in which the stress never decays. So an elastic solid that's held in a strained shape will retain a stress as long as you hold it strained. The stress will never decay. The key thing about these complex fluids is that the relaxation time is typically sluggish and commensurate with human observation. So, for example, a second, but it can be much shorter than that, or it can be much longer, but it's typically on a timescale that we humans can watch comfortably. Now, where does that timescale come from? Well, just as in a simple liquid such as water, the molecules there are rapidly jostling around under Brownian motion, so also in these complex fluids, the suspended mesostructures, the polymer chains or the rod-like molecules, are constantly reconfiguring, changing configuration under the influence of Brownian motion. But because they're so much bigger than water molecules, and in this case of chain-like polymer molecules here, they're also entangled with each other. And so the timescale for these molecules to refresh their configuration and thereby relax the shear stress that's produced in them at the time the strain is applied is very much longer. And it's that timescale for the reconfiguration of the substructures is the timescale on which we see the stress decay. I'd like at this point, just because this concept of viscoelasticity crops up so much, to ask if there are any questions. And could I also just ask the organizer to confirm that the line is still good, just because we had those problems earlier on. Can you still hear me? Is the line okay?
Yep.
Okay, thank you. Are there any questions so far?
No, I don't see any.
No. Okay. All right. Thank you. Okay, so that's the concept of viscoelasticity. So the third concept beyond softness and viscoelasticity that I mentioned a couple of slides ago is that it's easy to drive these complex fluids into nonlinear flow regimes. So we've already talked on the previous slide about an experiment in which we take a sample of material sandwiched between plates, and then at some time zero, suddenly just move the top plate by a small amount compared to the bottom one, and then hold it in that slightly moved position for all subsequent times. We're now going to think of a related but distinct experiment where at time zero, we start the top plate moving relative to the bottom one, and we move it to the right for all subsequent times at a steady rate. So in this case, we're constantly shearing the material by constantly moving this top plate relative to the bottom one. Now, of course, in this slab as sketched here, the top plate would eventually fall off the end of the bottom one. This is actually usually done in what's called a curved device, where you have large concentric cylinders, and here we're just seeing a little sector of those cylinders. Nonetheless, let's just think about our planar geometry here. So we're moving the top plate at some speed d by dt of L, which is a constant relative to the bottom one. When we normalize that by the gap between the plates, that gives us something that has units of inverse time, and that's known as the shear rate. So it's, in other words, the rate of change more or less of how quickly the angle here is changing. Now, the usual experience, or at least the usual assumption, although we'll see later on that that tends to break down actually, but the usual assumption might be that a shear field establishes within the material that looks like this. So here's the top plate that's moving, here's the bottom one that's stationary, and at any height in the fluid, we show by a vector pointing to the right the speed at which the fluid at that height is flowing to the right. And then the gradient of this gives you the shear rate. Now, what we do at any given shear rate here is we track the stress that develops, the shear stress, that's the force in this direction on this plate that has its normal in this direction. We track the shear stress as a function of time, as a function of the time since the inception of the flow, so since the plate started moving, and we wait for it to reach, at long times, a steady value that no longer depends on time, but it will depend on the shear rate. So this curve of the shear stress, so that's the force in this direction on this plate that has its normal in this direction, as a function of the shear rate, so the speed with which the plate is moving to the right normalized by the gap size, then gives you what's called the steady state flow curve. And this is one of the most commonly measured entities in rheology, steady state rheology. Now, typically in that flow curve, you will see two different regimes according to whether the shear rate is slow or fast. Now, what do we mean by slow or fast? Well, recall that this shear rate is indeed a rate. It has the units of inverse time. So what else do we know about that has units of inverse time? Well, that's in fact the relaxation time that we just characterized here in linear response. So typically, if the shear rate is very slow compared to the intrinsic rate at which these mesostructures refresh their configuration under the influence of Brownian motion, then effectively in shearing the material, we're just riding along on these Brownian reconfiguration dynamics that are there anyway, so we're not perturbing them. And so in this case, the shear stress is linearly proportional to the shear rate. And the slope of this line then characterizes the viscosity, or in fact, the what's known as the zero shear viscosity, because it's measured in the limit of slow rates. So here we have what's called Newtonian behavior, where the shear stress is linearly proportional to the shear rate with a slope of that gives the viscosity. But then on the other hand, when we shear at a fast rate compared to the intrinsic rate of the mesostructures reconfiguring themselves, we then start to actually interfere with that process. So rather than just riding along on it and measuring it, we're actually fundamentally altering the dynamics of these polymer chains, maybe even altering the structure by forcing them to all be aligned, for example. And so then we typically see then a regime of nonlinear response in which the reorganization of the mesostructure then feeds back on the flow in a nonlinear way. And so the shear stress is no longer linearly dependent on the strain rate. In this case, we see so-called shear thinning behavior, where the stress divided by the strain rate becomes smaller the faster you shear the system. And this is called then non-Newtonian response. And there's a whole discipline called non-Newtonian fluid mechanics that's devoted to the study of these kinds of non-Newtonian fluids that respond in this nonlinear way. Okay, so we've talked about two different shear experiments. One is the small amplitude step strain, where we watch the stress decay, and then another one where we shear the system at a constant rate. Okay, the fourth property that I listed a few slides ago is that these complex fluids typically have non-zero so-called normal stress differences. And so to talk about these, let me define the axes that I'll be using throughout the talk. So we've discussed this case where we have a sample of fluid sandwiched between plates and the top plate is moving relative to the bottom one. So I'm going to, throughout the talk, define the flow direction. That's the direction of overall flow. So the direction in which the top plate is moving, I'm going to call that X. I'm going to call the direction in which there's a gradient in the velocity profile between the plates, the so-called flow gradient direction, and I'm going to denote that Y. And then the direction that looks rather neutral here, where so far we're suggesting nothing is changing into the direction of the screen, Z, that's called the vorticity direction. Now, the component of the stress that we've talked about so far is the shear component. So as I've said, that's the force in the X direction across per unit area across a plane that has its normal in the Y direction. So that's the stress that I've been plotting, for example, on these flow curves so far, the XY component. Now, a feature of these complex fluids is that because in shear, the mesostructure can become arranged anisotropically. So, for example, the polymer chains can get extended out and oriented along the flow direction. Liquid crystalline molecules can also become oriented in the flow. And as a result of that anisotropy, the material develops so-called normal stress differences. So sigma XX then is the force per unit area in the X direction across a plane that has its normal in the X direction. So the plane is arranged this way, its normal is in the X direction, and the force is in the X direction. That gives you sigma XX. Sigma YY is the force in the Y direction across a plane that is arranged this way and so has its normal in the Y direction. And the so-called first normal stress difference is then sigma XX minus sigma YY. Similarly, we can think of a second normal stress difference, which is sigma YY minus sigma ZZ. These are respectively denoted N1 and N2. The reason that we think of differences rather than absolute values is that there's also a pressure in here, but we're usually thinking about incompressible flow. So that pressure is just then essentially a multiplier that adjusts itself to enforce incompressibility. So we're only interested in normal stress differences and not the absolute value of that pressure typically. Okay, so the fifth property that I mentioned a few slides ago is that these complex fluids, in fact, their behavior in flow can be so nonlinear. We've already talked about the fact that we can see nonlinear response, but it can be so highly nonlinear that, in fact, as a result of shear being applied, you can drive the system actually through a phase transition, a non-equilibrium phase transition that's induced by flow. And so then to see indeed a transition, these are sometimes also called flow instabilities. So in the context of a liquid crystal, so a liquid crystal has long rod-like molecules suspended in a solution. And there are, well, many different states actually, but two that I've drawn here. One is an isotropic state in which the rods point every which way. And another one is a so-called pneumatic state where these rods have all lined up with each other. Now, it's possible to get an equilibrium transition between an isotropic and a pneumatic state by, for example, dropping the temperature or by increasing the concentration of the rods. With nothing to do with shear at all. Here we're thinking, though, of transitions that are induced by shear, and indeed it's possible to induce that phase transition by not actually changing either the temperature or the concentration, but simply by shearing the system. And that's intuitively reasonable because when we apply a shear by moving the top plate relative to the bottom one, you imagine the shear that's applied essentially knocks these molecules somehow flat in the direction of the shear, and that causes a shear-induced transition from an isotropic to a pneumatic state. So that's just one example of a flow-induced phase transition. There are many, many more. And on this slide, this is not any sort of attempt at any rigorous classification at all. In fact, quite the contrary. It's just 6 different examples of the whole zoo of very wide-ranging examples of flow instabilities that we can find in complex fluids. So I've already talked about, in a liquid crystal, the idea of a flow-induced isotropic pneumatic transition where rod-like molecules that are initially pointing every which way line up. In a surfactant, we can see a transition from, so we have here surfactant molecules, each of which has a head group that likes to be next to water and a tail that doesn't. And when you put them into solution, they can form bilayers so as to hide the tail groups away from the water. So the end groups, the circular head groups here are the ones that are facing the water. These are basically, in essence, like our cell membranes. And then in this case, if we shear this so-called lamellar phase, these lamellae can all roll up into concentric onion-like structures that are shown here, which can then also order themselves in flow. In the context of a cross-slot, which is not now actually a shear flow, but here you have fluid in a four-armed flow device with arms left and right and up and down, and you have fluid coming in from the left and the right, so in from both directions here and then going out at the bottom and out at the top. Now at low flow rates, you typically see a four-fold symmetry, but at high flow rates, that symmetry is broken. So that's another example of an instability that occurs there in an extensional flow. You can see something called viscoelastic turbulence. So here we're looking down on a sample of a polymeric fluid that's being sheared between two concentric cylinders by rotating two circular plates, and it's being sheared by rotating the top plate relative to the bottom one. And at a low rotation rate, everything looks laminar, whereas at a high rotation rate, everything looks turbulent. Now, this is turbulence here, but it's not now turbulence arising from the inertial so-called V dot grad V term. I think you'll have encountered the Navier-Stokes equation already, but it arises due to the inherent nonlinearity of the way the polymer chains respond to the flow. An example that we're going to talk about much more throughout the rest of the talk is the phenomenon of shear banding, where an initially uniform shear field can undergo a transition to form two different shear bands with a high shear rate and a low shear rate. These are all bulk flow instabilities. As I've said, the final part of the talk will be devoted to surface flow instabilities. So here we see a very unpicturesque example where what we have here is a gap here that's filled with fluid, and that fluid is being sheared by spinning round this top disc here relative to the bottom one. Now, at a low rotation rate, the fluid remains nicely confined within the gap and its edges have been nicely trimmed to start with. But at a high enough flow rate, you can see this goo that basically exudes out of the side of the gap here. So there's been an instability that's happened as a result of that's happened at the surface where the fluid meets the outside air. So as I say, this is no attempt at all at anything like a rigorous classification. The opposite, actually, it's just intended to show how many and varied these kinds of instabilities or transitions that are induced by flow can be in complex fluids. Okay, so that concludes the brief introductory overview of complex fluids. I'll just pause to allow any questions if there are any. Okay, so let's now move on to, hello?
There's a couple questions. Hold on, please.
Thank you.
So the phase transition you talked about, are they like all first order phase transitions?
No, not necessarily. You can have continuous transitions or indeed first order transitions, and really that varies according to the transition. Yeah.
So the liquid crystal one is like a first order. Which of these transitions are second order?
Well, in the context of turbulence, there's that. For example, there's a debate that's raging there still, I think, although I haven't followed it recently. So you can find viscoelastic turbulence in geometries that have curved streamlines, and in that case, you would get the transition by what's called so that would be essentially of the form of a pitchfork bifurcation, where as you change the flow rates, the branch would become unstable, and it would then take you to a very nearby state that has, for example, an initially homogeneous state would then go to a roll-like state that's very nearby the one that you started with. That's what happens in flows with curved streamlines. In flows, on the other hand, with straight streamlines, it has been predicted that you can see what's called a subcritical instability, where instead there's a foldback, and the initially uniform state then changes discontinuously to a state that's a very long distance away. So there's essentially a whole zoo of different kinds of transitions that occur in systems.
Thank you very much.
I think there was another question. Is that right?
I have a question about the viscoelastic turbulence you mentioned. I just want to make sure the viscoelastic fluid doesn't necessarily mean that the viscosity is large, but simply for example, their stress and the strain relation is different from the Newtonian fluid. Am I understanding correctly?
Yeah, so as we talked about, there's a relaxation timescale in systems, and the viscosity actually is defined. Well, you can motivate what the viscosity should be by multiplying the relaxation timescale by a modulus, which is the modulus that you would see in a very fast perturbation experiment. So that tells us about the viscosity, but you asked about when the transition sets in. And in fact, the transition tends to set in when the flow rate multiplied by the relaxation timescale is greater than 1. So that's in a sense a different thing from thinking about the viscosity, because the flow rate times the relaxation timescale, which is something that's called the Weisenberg number. So that's a dimensionless number that crops up very widely in rheology. These transitions tend to set in when the Weisenberg number is greater than 1. Yeah.
Okay, I'll see more, and thank you for your explanation. Thank you.
Okay, but actually also to add to that, of course, we also know that fluids can show a transition to turbulence regardless of Weisenberg number at a high Reynolds number. And there, what you're thinking about is the value of the viscosity compared to the fluid density, then also normalized by various length scales and so on. And the kind of turbulence that we're thinking about here, although this has been categorized in the whole plane actually of Reynolds number and Weisenberg number, the kind of turbulence that I'm at least drawing there, which is a diagram taken from a paper by Ron Larson, is actually intended to be turbulence at an essentially negligible value of the Reynolds number. Yeah.
Okay, we have one more question.
Okay.
Talking about the relaxation time, does it mean that any fluid can be seen as a Newtonian fluid depending on the shear rate, or vice versa? So depending on the shear rate, that it is then a non-Newtonian fluid?
Well, that's a very interesting question. Yes, you would think so, going back to this drawing here, this sketch here, because as you would correctly say, if you shear it slowly enough, you would expect to get into a regime here where, so long as you're shearing slowly, compared to the inverse relaxation time, you're always going to get into this regime of linear response, where, as I said, you're not fundamentally changing the dynamics, but you're just riding along on the dynamics that are already there. That's fine, unless you think of a material where this relaxation time is in some sense infinite. And then, of course, this notch here moves right down to the origin, and you have nonlinear behavior right from the get-go. So what kinds of systems can we think about where the relaxation time might be infinite? Well, they're typically things like glassy systems. So that might be a colloidal suspension, where you have glassy behavior above typically a packing fraction of 0.58. If more than 0.58 of the space is filled with colloidal particles rather than solvent. That's the so-called thermal glass transition, or you can think of jammed suspensions of soft particles where you have a jamming transition above 0.6. Oh, I've just forgotten the number off the top of my head, 0.64, I think it is. Depends a little bit anyway on the polydispersity. So things like foams and emulsions, for example, typically have a yield stress. And in fact, we're going to see an example of a yield stress a little bit later on. So a yield stress material, then the flow curve would start at zero shear rate, actually at a non-zero value, and go up from here. So you would never have, that's nonlinear or non-Newtonian right from the get-go of zero flow rate. And then the counterpart in negative shear is, it looks like this. There is another example actually, which is not quite as extreme as a yield stress behavior, where you have a non-zero yield stress and then flow, but you can have something called power law fluid behavior. And so this is where the shear stress sigma goes as gamma dot to the power 1. You can have the shear stress sigma going as gamma dot to the power alpha, where alpha is less than 1, but greater than 0. And that also actually has an essentially infinite viscosity in the limit as you get down to very slow shear rate. Yeah. So thank you. Thanks for the questions. Are there any more questions? Does that answer your question?
Okay, I think that's it for now.
Okay, thank you. Well, good, I'll carry on. Feel free to interrupt with any further questions as we go. And I'll pause again in a few minutes to invite any more questions too. Okay, so we've given a basic introduction to complex fluids. Now we're going to talk about how we model them theoretically. So before diving into any equations, I just want to talk a little bit about the basic philosophy that at least the sort of school that I originated from, which is that of condensed matter physics, takes to modeling the flow behaviors of complex fluids. So the basic idea is that if we're interested in the macroscopic properties, such as, for example, the mechanical or rheological properties, such as predicting the viscosity, that is the ratio of stress and strain rate in a system of complex fluids, then the basic philosophy that we're going to adopt is that these macroscopic properties typically depend on the dynamics only at the coarse grained level of polymer chains, rod-like molecules, for example, and don't depend on the precise chemical detail of the atoms of which those chains are made up. So in the context of polymers, so I haven't actually said explicitly, I guess many of you already know, polymers typically are long chain-like molecules, which I've just drawn here as a squiggle, but these are actually made up of many identical chemically repeating and chemically bonded subunits called monomers. And which polymer you have depends on what monomers you have. So you can have polyethylene, for example, that's lots of ethylene monomers grafted together, polybutadiene, polyisoprene, and so on. And the idea is that the viscosity then only depends on the macroscopic properties at the level of the overall chain, independently of the chemical detail of whether you've got butadiene or whether you have ethylene monomers. So for example, if we have linear chain-like polymers, then we find that the viscosity goes as a power law of chain length. On the other hand, if we change the topology of the molecule to introduce a branch point to get a star polymer, we then typically find the viscosity goes as an exponential of the chain length. And again, that doesn't depend on the precise chemical detail of the monomers that make up the chains. So in other words, from our perspective, a polymer molecule is a piece of string, and we're interested in the statistical mechanics of lots of entangled pieces of string, molecular pieces of string undergoing Brownian motion. So in other words, what we're concerned with in trying to model the flow properties of these materials is the non-equilibrium dynamics of polymer chains or rod-like molecules in flow. Okay, so that's the basic philosophy. Now let's try and put that into a slightly more mathematical framework. So before we worry about how to model the flow properties of complex fluids, how do we model the flow properties of fluids? And I think you will have encountered this already in your lectures. I had a look through some of the earlier lecture notes, but just in case anyone's not been here throughout, and also to make these lectures, I guess, complete within themselves. So the way that we model properties of just thinking about ordinary fluids, not complex fluids to start with, at a continuum level is using the so-called Navier-Stokes equation. So this is essentially just applying Newton's second law at the level of individual fluid elements, where any fluid element is large enough to contain many molecules of the constituent fluid, but is small enough that the basic fields of velocity V and pressure P are uniform can be defined on so there are enough molecules that you can define a velocity and a pressure on the scale of any of these elements, but these elements are also small enough that the velocity and pressure don't vary over an element, but do vary on a much slower length scale over the flow as a whole. So at the level of those fluid elements then, to each fluid element, you apply Newton's second law, and that says that mass per unit volume multiplied by acceleration is the sum of the forces that act, and those forces are divided into viscous forces. Those viscous forces occur when you have fluid elements sliding past each other, and they have a dissipative drag past each other that's set by the viscosity of the fluid, which we denote eta. And then we have also forces due to pressure gradients. An obvious example, you can think of driving a fluid along a pipe by applying a pressure drop per unit length along the pipe. Okay, and then we're thinking here typically about incompressible flow where the divergence of the velocity field is 0. I haven't actually explicitly written that down, but that is then what sets the pressure field P. The pressure adjusts to ensure that the flow remains incompressible. Okay, so that's modeling the flow properties of, for example, water at the continuum level. Now let's think about how we extend that framework to model complex fluids. Well, the idea is that in any little fluid element, you have just the forces that we had before for water, because typically you have some watery solvent in the backdrop anyway in any complex fluid, but you also have these suspended mesoscopic substructures. And again, in any fluid element that's defined to be large enough to contain enough of these that you can do sensible averages over those substructures also contribute a stress, and that stress is viscoelastic in the way that we've already talked about before. Remember the step strain experiment. So we have a viscoelastic stress sigma, an additional stress that's due to these mesoscopic substructures. Now, typically that viscoelastic stress depends on some variable or multiple variables that characterize the arrangement of those substructures. So in a liquid crystal, there's a tensor object, which is actually typically denoted Q rather than W here, which characterizes whether the molecules are pointing every which way, in which case Q would just be the unit tensor, or whether they're lined up with each other, in which case Q would have different elements along its diagonal in the frame where it is diagonal. So that might be an orientation. W might be the orientation tensor Q in the context of a liquid crystal. In the context of polymer molecules, you might define a variable that tells you about the direction in space of little elements along the backbone of the polymer. That variable is often actually denoted W, as I've denoted here. So that gives you a measure of the molecular strain. The variable may not be a tensor, though. It may be a scalar. For example, in the worm-like micellar surfactants, which we'll encounter in more detail in a moment, typically the stress would depend on how long the micelles are, and there you just have a scalar variable. So I've just chosen those to illustrate the fact that in general, the viscoelastic stress in the material depends on the substructural arrangement of the mesoscopic substructures. And then what we need is an equation of motion that tells you how those substructures, how those variables characterizing the substructure, and of course you'd have a separate equation for each of the relevant variables, and they in general be coupled together. You need an equation for how that responds to an applied flow, and we characterize the applied flow by the velocity gradient tensor. That's the gradient, the tensor that you construct out of the gradient of the velocity. And so then that you calculate then the viscoelastic stress that appears in here, and then typically what that does is feed back on the flow field in a nonlinear way. Okay, and this equation of motion for the mesostructure is typically a nonlinear partial differential equation of reaction diffusion type. So I've not represented it here to look like a diffusion equation. It looks like it's entirely local here with just reaction-like terms. But of course, I've not defined whether this operator is local. If you want to think of n as being local, you could add a diffusion term on here that goes as some diffusion coefficient grad squared W on the end, for example. Now, for those of us who are used to thinking about inertial instabilities like conventional Reynolds turbulence in a conventional simple fluid, there's just one more mental change of mindset to make, which is actually that the inertial term, the mass times acceleration term, typically is small for the flows of complex fluids that we're interested in. The Reynolds number is small, and so typically we set the v dot grad v term to the inertial term on the left-hand side here to 0, and so we then have not the extended Navier-Stokes equation, but just the extended. So this would be the Stokes equation on its own, but we've extended it here with a viscoelastic stress, and that's typically 0. Now, in conventional simple fluids such as water, the onset of turbulence would have been determined by the nonlinearities that are contained in this inertial term. I'm sure you'll have met this before. This is a slightly peculiar time derivative that is partial d by dt plus v dot grad, and that allows for the change of velocity with time in a fluid element that's moving from place to place in the flow. And that nonlinearity v dot grad v that's hiding in this term here is the one that gives rise to funny transitions like turbulence. Now here we've set that term to 0, so you might say, well, therefore we don't expect any transitions in complex fluids because that nonlinearity is gone. But of course here there's a whole extra source of nonlinearity, which is the way that the mesostructure responds to the flow and how that feeds into this force balance condition here. Okay, so that's the equations of complex fluid flow written down in a very generalized way. Now I'm just going to present one particular example, just to highlight that in a pedagogical way. The particular example that I'm going to think about here is the so-called worm-like micellar surfactant. So surfactants comprise molecules that are so-called amphiphilic. So what does amphiphilic mean? Well, it means they have a head group that's usually polar, or in other words, likes to be next to water, using rather anthropomorphic language, I'm sorry, and a non-polar tail group that doesn't like to be next to water. So when you put many of these solvent molecules into aqueous solution, then depending on the conditions, on, for example, how big the head group is compared to the tail group, you can get these molecules assembling into various structures so as to hide their non-polar hydrophobic tail groups away from the water, so that only the hydrophilic head groups are next to the water. So as I say, depending on the conditions, you can get either so-called spherical micelles or cylindrical micelles, or the molecules can layer into sheets where we have the heads arranged here on this sheet and then the tails in between in this sort of bilayer sandwich here, which, as I say, is a rudimentary cell membrane. These membranes can form various more complicated phases, such as plumber's nightmares phases, so-called here. Let's just think for today, for the purposes of this pedagogical introduction to the rheology of complex fluids, let's think about worm-like micellar surfactants, which have actually probably of these been the most intensively studied from a rheological viewpoint. So let's think about then an ensemble of worm-like surfactants. So when we look at a slightly more coarse-grained level, let's just represent each of these wormy surfactant micelles, so-called, as a squiggle, which now starts to look actually a little bit like a polymer molecule. And you might think that then understanding how a whole entangled mess of these worms that are entangled with each other, how that responds to flow, is a hopeless task. But actually, what we do here is take a mean field approach, where we reduce what is the n-body problem to a one-body problem, where we focus on a single worm. And these are actually ideas that were developed in the study of entangled unbreakable polymers. So if we focus on a single worm, and then ideas that were developed back in the 80s by Doy and Edwards and Dejean and others, is to, in focusing on a single worm, the idea is that you replace the effect of all the surrounding worms by a mean field tube that represent the fact that this worm of interest that we're focusing on, the one body problem essentially, sits in the mean field where it's entangled with all the others, and those entanglements constrain the motion of this chain of interest, constrain the motion at least orthogonal to the chain, but the worm can snake backwards and forwards along this tube. So the dynamics are then heavily constrained. And how's it going to then escape from that tube, as it needs to, under Brownian motion, to reconfigure? So imagine you've just applied a strain to this and all the worms have become slightly strained in a shear-like way. In order to relax the shear stress that ensues, that results, you need these worms to refresh their configuration. So in other words, they need to escape the tube that's become slightly oriented by the shear. And the way that they escape the tube is by a process known as reptation, which is basically a curvilinear snaking backwards and forwards along the backbone of the tube. That process of reptation was, as I say, developed back in the 80s. And then in these micellar, in these worm-like micelles, these are what's called so-called living polymers, because these micelles are constantly being formed and then breaking again under the influence of Brownian dynamics. And that breaking takes the form of the worms constantly breaking and then reforming. So there's another, we don't only have reptation, we also have so-called reaction, which corresponds to these worms breaking and reforming. So these microscopic processes of reptation and reaction were formulated by Mike Cates back in the late 80s and early 90s into a model. And I'm writing this down not with the intention that we should understand all the details. In fact, I haven't recently read all the details here, but simply to illustrate that this now fits into the basic structure of the equation set that I illustrated previously, where you have an extended Stokes equation with a stress from the mesoscopic substructures. You have a solvent term and a pressure term. You also have the divergence of the velocity of zero, the incompressibility. And the viscoelastic stress then depends on a mesostructural variable, which here is a tensor that characterizes the deformation of the worms. And it does so by defining a tangent vector at any point along a worm and constructing a tensor out of the product of the outer product of the tangent vector, and then you average that over the probabilistic distribution of these in the sample as a whole. That then gives you a tensor that characterizes the micellar deformation, and that has dynamics in flow, which takes the form of this nonlinear equation here. It looks rather intimidating, but actually if you switch off all this stuff that knows about flow here, it simply says that this relaxes on this. Here's the familiar viscoelastic relaxation timescale here. It relaxes onto the isotropic unit tensor on that relaxation timescale when you would then have no stress, whereas the presence of shear stirs up these worms or disturbs their orientation and results then in a non-zero viscoelastic stress. Okay, so then you can work through the predictions of this so-called reptation reaction model, which, as I say, I'm just presenting as one example of a nice example, actually, where you can write down a constitutive equation for the mesostructure of a complex fluid and get predictions that have been verified experimentally. So now let's have a look at the predictions of this reptation reaction model in the two particular rheological experiments that I introduced earlier when I was giving the overview of complex fluids. So the first experiment that we talked about was this one where you take a slab of material, now a worm-like micellar surfactant solution, so lots of wormy micelles in a watery solvent, and at time zero, you suddenly shear strain it by moving the top plate a small distance to the right relative to the bottom one, normalize it by the gap size, that gives you the shear strain, and you apply that at time zero and you hold the sample strained, so you hold this top plate in its move position for all subsequent times. You get some shear stress generated, force in this direction per unit area on the plate that has its normal in this direction, and the stress then decays on some time scale. And in fact, in these worm-like micellar surfactants, it's predicted and has been seen experimentally to decay in a so-called mono-exponential manner, so just a single exponential, with a relaxation timescale that is actually the geometric mean of the timescales associated with reptation, or so-called breakage, and the timescale for disengagement from a tube by this process of reptation. It's actually rather rare in complex fluids to have such a simple mono-exponential stress relaxation. Typically, for example, in unbreakable polymers, you would have a much slower, often a power law decay of the stress because you have things happening on lots of different scales as different bits of the molecule manage to escape their tube, for example. Similarly, in a compressed emulsion where you have tightly packed soft particles compressed together, you would there typically see power law relaxation as well, to do with a glassy-like or jam-like disorder in the system. But nonetheless, these worm-like micellar surfactants are a very nice example where you see a mono-exponential relaxation. So this is this first kind of rheological experiment that I introduced earlier on. Now let's think about the second kind. That is where we take a slab of material, here worm-like micellar surfactant, between two plates. And at time zero, we switch on a shear flow by starting the top plate moving relative to the bottom one. And we indefinitely move it at some speed d by dt of L to the right compared to the bottom one. Normalized by the gap size, then we get this entity, the shear rate, which has units of inverse time. And the usual experience, or at least the usual assumption, although we'll see in a moment that's dangerous, is that the shear field that establishes is homogeneous. So the shear rate, the spatial gradient of the velocity, is uniform across the gap. And the reptation reaction model predicts a shear stress as a function of shear rate, which increases and then shear thins. So we have Newtonian behavior here, where the shear rate is less than this geometric mean of the times, the breakage and the disengagement time. It shear thins, and then it shear thins so much that the stress is actually predicted to decrease as a function of increasing shear rate, and then it increases again. Now, this was really a puzzle when this was first predicted, because what on earth is going on in this regime? Because what this is trying to tell us is that a faster flowing system has less stress, which sounds rather crazy because it's the stress that resists you from flowing faster generally. So what on earth is going on here? And in fact, it was realized in this paper here in 1993 in Physical Review Letters that a region of negative slope in the constitutive curve is actually unstable. So it signifies that an initially homogeneous shear flow, which is the assumption that we've been making so far throughout, is actually going to be unstable to forming shear bands, where you have now a portion of the fluid flowing with a high shear rate and a portion flowing with a low shear rate. And in fact, the shear stress due to force balance has to be uniform across the gap and so common to both the bands. So the only thing that's different is the shear rate in each band. And now if we imagine tracking the overall applied shear rate, gamma dot, sorry, I've missed that off the axis here. If you progressively increase that through this window here, the shear stress, which is common to both the bands, stays constant. So we now, instead of having the loop, what we measure in the steady state flow curve is this plateau. So the stress remains constant, as does the shear rate in each band. And the only thing that adjusts is the relative amount of the bands. So in other words, the position of the interface. So as the shear rate progressively increases here, you have more of the high shear band and, relatively speaking, less of the low shear band, such that when you get right to this point here, the whole of the gap is filled by the high shear band and you've restored homogeneous flow on this branch here. Okay, so I presented that to you just almost as though it's a kind of fait accompli, that you will, if you start with, so what we're imagining here is starting with a base state of homogeneous shear, where the system has somehow managed to attain a state of homogeneous shear on this stationary flow curve, which you remember is the time-independent relationship between shear stress and shear rate. And I presented it to you as a fait accompli, that will become unstable to form a steady state that comprises then two bands, a high shear band and a low shear band. What I want to do now, in the spirit of a summer school, and I think given the pace we've been going, this may fill the rest of the lecture, actually. I think in the interest of my voice and also concentration over a Zoom talk, I'll just do this calculation and then I'll leave lots of time for questions and we can start tomorrow on the active fluids. So what I want to do now is just present, as I say, in the spirit of a summer school now, a pen and paper calculation. If I'd been with you in person, I would have been doing this at the board, but I did it effectively at the board on my computer the other day, and I'm now going to show you the handwritten notes that would have appeared in front of you as I talk through it.
Suzanne,
hello. Yes.
There's a question before you go into it.
Yes, thank you very much. Yeah.
So this shear stress that is common to both of them, the gamma dot low and gamma dot high, is it like the equal area construction in thermodynamics? Is it? I mean that.
Yeah.
So
thank you. Sorry, carry on.
No, so it can be any line between those, right? So the specific line that is common to them both should be specific. So I think it reminds me of Maxwell's construction. So just.
Yes, thank you. That's an extremely good question. And in fact, that was a question that was a very active research question back when this effect was first predicted. So the question was, well, is this like a Maxwell construction where you have equal areas here of shear stress? So for those of you who don't know, there's something called the Maxwell construction for phase coexistence, and transcribing that into this language, it would say that the basic question is, well, what is the stress at which these bands coexist? In principle, you might think it could be anywhere in this window between this maximum and this minimum. If this were to obey a Maxwell construction, then what that would say is that you determine this stress by enforcing that this area here under this loop between the horizontal line and this loop and this area here has to be the same. And that was originally proposed, but it was in fact shown not to be the case. And the reason for that is that actually the Maxwell construction comes out of in the context of equilibrium phase coexistence, which is where the Maxwell construction comes from. So we can either, by the way, think about the coexistence of two fluids, or we can think about the pressure volume also phase transition, about a Maxwell transition in either of those cases. In either of those cases, it arises from minimizing the free energy. So you can show that that's what you do in order to get this equal areas construction. Now, in these flowing systems, of course, by virtue of the fact that this system is constantly being sheared or stirred from the outside, it's out of equilibrium. And so the state doesn't follow by minimizing the free energy. So this was a great puzzle of, well, if you don't have a free energy to minimize, how do you have an equal areas construction? And in fact, it turns out that you don't have an equal areas construction, apart from in some very simplified scalar models. Actually, it turns out in the model that I'm about to show you, you would get an equal area construction. But most of these tensorial models are what's known as non-integrable, and you don't get an equal area construction. So there was a great puzzle to resolve of, well, in the absence of an equal area construction, what sets the height of this coexistence stress here? And this was something that was resolved in some really beautiful work that Peter Olmsted did actually in the early 90s. I was very fortunate later on to be a postdoc with Peter in the early 2000s. So he did some work also around a similar time. Mike Cates also did some work on this too. And what they showed is that, so when I was introducing, excuse me, whizzing back quickly through slides, but I think it is useful just to show you this. What I discussed earlier on, just briefly, is that this equation of motion for the mesostructure in the fluid typically is not just spatially local as it might look like here, but it's actually non-local and it has a diffusive term, so an L squared grad squared W. And in fact, it turns out, so that L squared grad squared W, by the way, is what is the term that tells you about the structure of this interface that you get between the bands. So you don't just have a step function going from the low shear rate band to the high shear rate band. You don't really get step functions in physical reality and physical systems. There has to be some slightly diffuse width, which is the width of the interface between the bands across which things vary. And it's that grad squared term that tells you about the structure of that interface. And in fact, it's that grad squared term that is, you need that grad squared term in the models. You need that spatial non-locality. And it turns out to be that tells you what stress you get this coexistence at. So this was really a great breakthrough in understanding shear banding and what stress you're going to get this coexistence at that was made, because in fact people had solved and got shear banded states on the computer in some of the early papers, theory papers on shear banding, but they got very, very peculiar things like the stress could vary according to the initial conditions that you used. And there's a particularly nice PRL from the, I'm trying to struggle to remember the date, it may be 1997, with Peter Olmsted and I think it was David Liu and also Robin Ball, where they talked about looking at the dynamical systems as a function of space, cast into the language of dynamical systems theory, about the kind of connections that you get between this phase and this phase. And they showed that if you're at a stress that's the wrong stress, so not the selected stress, you have a homoclinic connection where you would start, say, in the low shear phase as you go, as you start from this plate, quickly zoom through a pulse of high shear and then go back to a low shear phase. So sorry, in the language of shear, that will be low shear, high shear and low shear, but just a very thin sliver of high shear in the middle. Whereas on the other hand, when you're actually at the selected stress, you have what's called a heteroclinic connection, where you go from this low shear phase and then you arrive at this high shear phase when you get to the other side here. So thank you very much. That was a very good question. And that took us back to what was a very important debate in the early days of the shear banding literature. So the idea is the take-home message there is you need these spatial gradient terms. What I'm going to do actually for the calculation, just showing the instability that shear bands form, is actually I've thrown those diffusive terms away because they turn out not to be very important, simply in telling you that initially a homogeneous state will start to become shear banded, but they are crucial for selecting the ultimate banded state. Before I get into that calculation, are there any more questions?
I have a question. Is it so below gamma dot low, if I see the slope, which is much stronger than if I go to the regime of gamma dot high. So is there any particular reason for that, or can we understand it intuitively?
So actually, if the slope was much higher, you could imagine a state that it might have wrapped around this way rather than that way. But I guess to understand those slopes, I guess what you're asking is, well, what's happening inside the fluid that means that this has a higher viscosity than this one? So generally what's happened, so if we go back to think about, here we are, a vat full of entangled chain-like objects. Generally at low shear stress, as I say, you're just riding along on the dynamics that are there, so you haven't really done anything fundamentally to the structure arrangement. So the arrangement of these chains is more or less isotropic. Now, generally what happens by the time you're shearing at such a fast rate as to be over here, is that these chains have actually got quite strongly aligned with the flow. So in other words, they've got knocked flat somehow in the flow. And because in measuring in characterizing the shear stress tends to be maximal when the orientation is 45 degrees. Once they get beyond that, you effectively don't have anything to bite into in terms of cutting through the molecules in this direction to give you a shear stress. And so the shear stress is then much lower. So that's an argument in chain-like systems, similar argument in also in liquid crystalline systems as well. Yeah. Are there any more questions? My voice is struggling to hold out. I hope it will hold out for another 10 minutes or so.
I think that's it for right now.
Okay, thank you. All right, so what I'll do now is just go through, as I say, I would have done this at the board if I'd have been with you, and I'm sorry again that I can't be. But I'm now going to go through a pen and paper calculation in the spirit of this being a summer school, where I just go through the maths of how, so as I say, we're starting with a base state, which is a state of homogeneous shear, assuming, so imagine that we've started the system shearing at some shear rate, we've somehow magically got it to a state where the shear stress is a stationary, as in time independent function, and it's determined by the shear rate, but where it has a negative slope of shear rate with this homogeneous shear. And then what we're going to ask is, well, if we start with very small perturbations, small heterogeneities in the shear rate that are a precursor of bands about that initial state, do those precursors grow to eventually lead to a banded state, or do they decay? And what we'll show is that they grow in this region here, and they decay in this region here. Of course, that begs the question, well, what happens in these regions here? And we can talk about that a bit later if you want. But first of all, let's just talk about what happens in this region here. All right, so to do this calculation, let's go back to the basic equations that I introduced earlier on. So what's the basic structure of the equations of complex fluids flow? So we have what would have been the Stokes equation. So 0 is e to grad squared v minus the gradient of the pressure field, and then an incompressibility condition, which is the divergence of the velocity is 0, which I haven't written down. Without this term, that would just be the Stokes equation. We said that we need to extend that to account for the fact that in any fluid element, there aren't only these Newtonian viscous stresses, but there's also a viscoelastic stress due to the mesoscopic substructures. And that depends on a mesostructural variable W. And then we need a dynamical equation that tells us how W responds to a flow and how it relaxes under Brownian dynamics as well, which is somehow all contained in this N. In fact, very often, at least in writing down so-called phenomenological equations, you know, if you're really going to, the real aim in rheology, I guess, for a theorist is to write down these equations based on really understanding the statistical mechanics of the polymer chains and how they respond in a flow. You can actually make a lot of progress, though, in understanding the rheology of these systems by not necessarily doing that whole process of coarse graining over the dynamics of the polymer chains, but actually just writing down a so-called phenomenological equation for the viscoelastic stress. And if you do that, very often you take a shortcut where you don't bother writing down the mesostructural variables, but you just directly write down an equation of motion for the viscoelastic stress little sigma, distinct from the total stress big sigma. And that generally has the form of relaxation terms with some timescale tau, and then terms that make the stress build up the stress in the presence of a flow. So in the spirit of a simple phenomenological equation, I'm going to take that shortcut and not worry about the mesostructural variables and just write down an equation of motion for the viscoelastic stress. So in other words, we're going to have the Stokes plus equation, as I've called it, this Stokes equation with the additional stress, and then an equation of motion for the stress. Okay, now let's specialize to the problem of shear banding, which, at least for now, I'm treating as an essentially one-dimensional problem. So this initial state here is 0-dimensional, actually, in the sense that the shear rate is uniform across the gap. Here we have spatial variation in the one dimension, that is the spatial gradient dimension y. And we're going to specialize to consider then problems where the fluid is only flowing in the x direction. So the fluid velocity vector is only along the x hat direction, the unit vector in the x direction, and there's a velocity field which only varies in the flow gradient direction y. So the velocity v, which is in the x direction, only varies in y, but in terms of space, but it can also vary as a function of the time t. Now the velocity gradient vector then only has a shear component. Now there's endless scope for confusion in the way that these models are written down according to the way you write what's called a rotational term. That you have to have a rotational invariance term, whether you write sigma dot grad v or the other way around, and it's transposed. Whether you think about this being y hat x hat or x hat y hat, I'm not going to go into that today. You might think it's funny I've written it y hat x hat, but that's the way that I usually write it. And then you have to make sure that you get this rotational term in the right form here. So with that technical aside, so the velocity gradient tensor only has a shear component, which I've chosen to write x hat, sorry, to write y hat x hat. And you have this velocity, which is in the x direction, which only varies in the y direction. And the spatial gradient of the velocity or the speed, as I've said, is the shear rate. And I'm going to denote the shear rate gamma dot, which is now a function of y and potentially also time. That function gamma dot has to average over the cell to equal the overall applied shear rate, which is the speed that you're moving the top plate normalized by the gap size. So even with such an applied shear, actually complex fluids would normally have not only shear stresses, but also normal stresses, as I talked about earlier on. In fact, for simplicity, I'm going to ignore those. So there's really a lot of simplifications in this calculation. So I'm only going to think about the shear components of the viscoelastic stress tensor, little sigma xy, which for notational convenience, I'm just going to denote little sigma, which depends on in general, on the flow gradient direction and also on time. So with that, now let's think about that simplification. So I'm going to just work through explicitly the Stokes equation here, extended Stokes equation is written in a tensorial form. In any given geometry, of course, then you need to extract the components of those tensors. So imagine we were thinking, first of all, about a two-dimensional problem. We're not, we're specializing to 1D, but just to show you that process that you would normally do. In fact, normally you would actually write it in 3 dimensions. I haven't bothered to do that here. But let's write down all the components in 2 spatial dimensions and then cross out whatever we've thrown away in making all these specializations here. So taking this tensorial Stokes equation, now in 2 dimensions, 2 Cartesian dimensions, writing down the components. So we have as the vector 0 on the left-hand side of the tensorial equation. So the x component of 0, if you will, bit of a funny thing to think about. So just another word 0, but this is the x component of the equation. So you have the x component of the divergence of the viscoelastic stress tensor, which is partial d by dx sigma xx plus partial dy sigma xy. You then have the x component of the eta grad squared velocity vector v. So you have vx and the grad squared operator, and you have the gradient of the pressure, which is d by dx of p. The y component of the tensorial Stokes equation is then 0 subscript y, so of course just 0. I just do that for my own notational just to keep it clear in my head which component I'm thinking about. So here we have d by dx of sigma, which you might in principle think is yx. This is actually a diagonal tensor, so I've also written it xy, plus d by dy sigma yy, and then eta grad squared of the y component of the velocity, v subscript y, and then d by dy of p. Now there are simplifications that follow. So we're thinking about flows only in the x direction, so we cross out vy, so all of this term immediately goes away. We're not allowing anything to vary in the x direction. Remember, we've said we've only got gradients in the y direction, so we can cross out this and we can cross out this. So then we have 2 equations, d by dy of sigma xy plus eta grad squared vx is equal to 0. That's the one that's actually important. We have one that we really, at least in this calculation, don't care about, which simply says that force balance tells you that the y derivative of the total stress YY component, which includes a viscoelastic piece and the pressure piece, has to, so sigma YY minus P has to have 0 gradient. Now that's well and good, but we don't actually really need to use that in this calculation. Okay, so for this geometry then, the Stokes equation, or the extended Stokes equation with the viscoelastic piece, is simply d by dy of little sigma, because recall sigma xy I've denoted little sigma, plus eta d by dy of v, that's this term here, so I've called v x v, is equal to 0. Now, d by dy of v is just the shear rate. So d2 by dy of v is just d by dy of the shear rate. So the extended Stokes equation just says that 0, or rather d by dy of the viscoelastic stress plus eta d by dy of gamma dot has to equal 0. So you can now integrate this up on the spatial gradient position y. So that says that because this is 0, you get the constant of integration, which is a constant, so it doesn't depend on y. So this gives you what I'm going to denote big sigma, which can't depend on y but can depend on time, is the sum of a viscoelastic stress plus a Newtonian stress, which is eta times gamma dot. So that simply says in any given fluid element at any position y, the total shear stress has to be the sum of the viscoelastic stress plus the Newtonian solvent stress, and those two have to add up to the total stress, which because of force balance can't depend on y. And you can see why that is, because on any rectangular slab of the fluid, the force is the stress at the top of it acting this way and the stress at the bottom of it acting this way. They have to be equal and opposite if there isn't to be a net force on that slab, because if there were a net force, that slab would be accelerating. So in other words, this is just force balance, in other words, that comes from doing the Stokes plus equation component-wise. So that's the first basic equation that we're going to use. So this is it just again, Stokes plus as just discussed, total shear stress is uniform, the sum of a viscoelastic and a solvent term. We now need a viscoelastic constitutive equation for the viscoelastic piece, and that's generally of the form of this horrible tensorial equation. I've specialized to only worry about the scalar form where we only worry about the shear component. So this is really a very severe and entirely unjustified approximation, but let's assume that we can just write down an equation of motion, which is general nonlinear. So this F is a kind of scalar counterpart of the N tensorial N before, which says that d by dt of the viscoelastic stress depends on sigma and on gamma dot. And I'm not here at the moment worrying about spatial gradient terms, although they are very important as in the answer to the previous question. Okay, so now what we want to do is use this simplified model. So these are the two equations that we're going to use, and we want to use that simplified model to show that when the slope of this constitutive curve, the total stress as a function of shear rate, when that slope is negative, a state of initially homogeneous shear, so we're starting with a state that's on this stationary constitutive curve, so it's stationary in the sense it doesn't depend on time, but it not depending on time, a solution not depending on time is not the same thing as saying as it's stable, because if you perturb it slightly, it then may start evolving and depending on time. So this is like the equivalent of having the cartoon would be a ball exactly balanced at the top of a hill. That's a stationary solution, d by dt is 0. It's not stable because if you just knock it very slightly from the top of the hill, it starts rolling down. So a stationary solution of homogeneous shear, initially homogeneous shear, with a relationship between stress and strain rate as prescribed here, we want to show it's unstable as a function of time t to forming when it's slightly perturbed away from this homogeneous state to starting to form shear bands, which are the ultimate time to infinity solution. All right, so let's now use these two equations to, what we want to do is use these two equations to look at two things. First of all, we want to look at the slope of this stationary constitutive relationship between shear stress and shear rate. Secondly, we want to ask, is an initially homogeneous state subject to perturbations? Do those perturbations grow or decay? So let's look at those two separately and then match them up later on. So first of all, let's look at the slope of this constitutive equation. So to do that, what we need to do is differentiate these two equations here. So I'm going to do that differential by writing them as total differentials. That really what we want is d sigma by d gamma dot. You could write that, but I'm just going to choose to write d sigma, d big sigma, d little sigma, d gamma dot. So differentiating Stokes plus, we get d big sigma is d little sigma plus eta d gamma dot. differentiating the constitutive equation. And remember, because we're thinking about an initial state of stationary homogeneous flow, stationary means don't worry about time, homogeneous means don't worry about space. So we're not worrying about either of them. So we've crossed out the d by dt. So differentiating the stationary solution of the constitutive equation, to do that, we need to take partial differentials of this functional form f. So f sub df by d sigma, which I've denoted f subscript sigma, times d sigma, f, so df, partial df by partial d gamma dot, which I've denoted f subscript gamma dot, times the little increment d gamma dot. Now, if we combine these, we get that d sigma by d gamma dot is, we just get eta from this term, and then from this term, we get d sigma is minus f subscript gamma dot over f subscript sigma. So this is a general expression for the slope of the constitutive curve expressed in terms of the partial differentials of this function that specifies the constitutive dynamics of the viscoelastic stress, its partial derivatives with respect to its two arguments. So we've looked at the first thing, the slope of the constitutive curve. Now let's look at when an initially homogeneous shear state is unstable to banding. So to do that, recall the governing equations, and we do now need to worry about time because we're looking at the dynamics of whether you get an instability taking you away from the initially stationary solution of uniform shear. So we're going to do here what's called a linear stability analysis, and I'm sure you'll have met this in other contexts before in this school, but we're going to assume a solution that comprises an initially uniform state of homogeneous shear that is stationary in time. So in other words, that's the state that we started with, that's homogeneous, uniform, and not depending on time. But we're going to add to it small perturbations that are the precursors of any shear bands. So now let's do that. Well, of course, actually, we can't add any perturbations that depend on y to the stress because we've argued that on general grounds that stress has to be uniform. On the other hand, we can have spatial perturbations to the, oh dear, what's happened? What? That's very confusing. I don't know what happened there. I'm sorry about that. So we can now add perturbations to the viscoelastic stress and to the solvent, to the Newtonian viscosity. So we decompose those into Fourier modes. Of course, there would be a sum over modes. I'm only representing one mode here. You actually, turns out these modes all uncouple from each other at the level of linear perturbations. So each mode we represent as a Fourier mode in the y direction. So sine waves or cosine waves with the appropriate boundary conditions in the y direction. The time dependence, once you've linearized the equations, turns out to be generally exponential. And then you have the prefactors, which is, so this is a small amplitude of the perturbations, and the relative size of those is specified by the eigenvector that would come out of the linear calculation. This omega here in the exponential is what's called the eigenvalue that will emerge. And what you want to show is if you get a positive eigenvalue here, that says that this grows as a function of time. And that says, therefore, that these small perturbations grow as a function of time to take you away from the initially uniform shear state and towards a shear banded state. So in other words, we're looking for solutions where we have at least one positive eigenvalue here across the K modes. Excuse me. So if we substitute the assumed solution into the governing equations and expand to first order in the size of the perturbations, so in other words, we just take this solution, substitute into this, and expand to first order in the size of these perturbations, we get a linearized form of this equation. Well, in fact, this equation is actually linear already, but we get a linearized form of this equation, and linearization involves taking partial derivatives of f with respect to its two arguments. So the two equations that you get is 0, remember no perturbation to the total stress because it has to be uniform, is a perturbation to the viscoelastic stress and a perturbation to the shear rate, and therefore to the Newtonian stress. And then d by dt of the perturbation to the viscoelastic stress then follows from the linearized form of the scalarized viscoelastic constitutive equation. We then simply combine these, and we get that d by dt of the perturbations to the viscoelastic stress, and of course, if the stress perturbations grow, the strain rate ones will too, is of the form of some eigenvalue, which is the thing that we want to calculate, multiplied by itself. So in other words, we're going to have exponential growth or decay according to whether omega here is positive or negative. And we know what omega is. It's f of sigma minus f of gamma dot divided by eta. We get that just from combining these two equations. All right, so we've now done these two calculations, A and B. We've shown that the slope of the constitutive curve is of this format here, and we've found the eigenvalue for the growth, if omega is positive, or decay, if omega is negative, of the perturbations. So we can now combine these, and it turns out then that the eigenvalue, very sorry, I don't know what's happening here. The eigenvalue is the slope of the flow curve times a prefactor, which is 1 over eta. Now, eta is just a positive constant. It's the viscosity of the Newtonian part. And then we have f subscript sigma. Now, it's possible to show in general terms that f subscript sigma is negative. The reason it must be negative is if you imagine a solution at fixed overall shear rate that you insist is homogeneous and you perturb it slightly, then if f subscript sigma weren't negative, then that perturbation would take the homogeneous solution off to infinity here or there. So f subscript negative has to be negative so that the viscoelastic stress dynamics are so-called on-diagonal stable. So if f subscript sigma is negative, this tells you that in order to get a positive eigenvalue here, that we get a positive eigenvalue if the slope of the constitutive curve is negative. So in other words, we've successfully shown that if you start with a stationary state of shear on the homogeneous constitutive curve, and then you add small amplitude, time and space dependent perturbations, they will grow in any regime where the constitutive curve has negative slope. And it's that linear instability that prefigures the start, that tells you about the start of perturbations that lead to shear bands. To then select the steady banded state, you would need to extend this constitutive curve to have plus a diffusion coefficient d2 by dy squared of sigma on the end, but I'm not going to go through that here, but you can read all about that in the papers by Olmsted, Liu and Ball from the 90s. Okay, so we've predicted then that the reptation reaction model predicts a non-monotonic flow curve, and so an instability and transition to shear bands. And indeed, we've talked that through in the context of worm-like micellar surfactants, which were some of the earlier systems in which shear banding was talked about. But since that time, actually, it's been shown more or less, well, that perhaps many or even most of the key classes of complex fluids show shear banding. So in other words, if you're going to study rheology, you need to be constantly alert to the fact that your flowing state inside the rheometer may not be homogeneous, but actually may be shear banded. I'd actually intended to get to the end of this section on rheology. I've got about another 5 minutes, but I've noticed we're up against the end of the slot, so I suggest, and my voice is giving out. So if the organizer wants me to, I can carry on to get to the end of that in 5 minutes today. Alternatively, I can just tack it on to the start of tomorrow's talk. So I'm happy to be guided by what you want me to do for that.
If you don't mind postponing that till tomorrow, because there's
fine.
probably some questions at this point. Are there some questions? Yeah.
I know you gave some examples in the beginning of what types of problems you would this might be relevant for, but can you give more specific examples of where this relation between sigma and the shear rate holds? Would it hold for, say, blood?
Where what relation? Do you mean a relation that's of this shape here?
Yes.
Yeah, okay. Yes, so as I say, the first, well, how to answer that? So what you try to do for any class of complex fluid is to derive on a microscopic footing. So thinking about the statistical mechanics of the polymer chains or the rod-like molecules or whatever, you try to derive a microscopically faithful constitutive equation, and then using that, you predict the shape of this relation. Now, actually, the number of examples where it's possible to microscopically predict a constitutive equation and then compute its predictions are still relatively small across the major classes of complex fluids. One of the earliest examples of successes in that regard was was the case of worm-like micelles, and that's where this first appeared. Actually, the original Doy-Edwards model of unbreakable polymers, entangled polymers, also predicts this region of declining slope. But there's been a debate raging ever since, and to some extent still is, about, because that prediction is made actually assuming that the chains are all of the same length and are monodisperse. If they're polydisperse, you might argue that this instability gets wiped out. And also there are other microscopic processes. It's a while since I've read the literature on entangled polymers, but there are other processes other than reptation known as, there's a breathing mode of the chain along the length, and then there's something called convective constraint release. And depending on the relative amounts of those processes, which actually you don't necessarily know a priori anyway, you may get a constitutive curve that's positively sloped or negatively sloped. So whether microscopic models of entangled polymers predict a negative slope or a polymer slope, or a positive slope, sorry, I think is to some extent still an open question. There are other examples actually in the context of liquid crystals. Now that's an interesting example. So in fact, tomorrow we're going to, I'll just flick forward to it. Tomorrow we're going to come across a constitutive model for the hydrodynamics of liquid crystals as a preamble to talking about active fluids. Now here you replace the W tensor by a Q tensor, and you get something that looks very intimidating, but is actually just of the same format that I've shown here. Now, what the constitutive curves look like for that model, that class of models, is not, isn't actually even as simple as this. Turns out that it goes up and then wraps back around itself and then goes up, but you can still nonetheless show that you get an instability in this region here. I'm trying to think of other classes of complex fluids where you can really compute on a microscopic basis that you get this negative slope. It's been shown actually that you get a region of negative slope, but in a rather different example where the flow curve isn't shear thinning, it's actually shear thickening. And then you get a region of negative slope and then it wraps back round that way. In that case, actually what happens is that you get bands forming not with layer normals in the gradient direction, but in the vorticity direction. And you get this kind of curve in what's called the discontinuous shear thickening transition in dense suspensions. And those have really been the topic of very active research, even in the last 5 years or so in the rheology literature. And so there's a model actually again by Mike Cates working with Matthew Wyatt, and also Mort, Den and Seto and Mari have shown using simulations that you do get that. So that's one way in which you can argue that it's there. Another way in which you can argue that this region of negative slope is there is if you experimentally for any given class of fluids is simply if you see shear bands forming, you might argue that, well, there should be a negative slope there, but it's not to say that you can necessarily write down a microscopically faithful constitutive equation and solve it. So sorry, that was a very long answer to a short question, but I think that's what you were asking.
I have a question.
Mm-hmm.
If we look at the bottom right picture on this slide, I can see the shear of the lower branch is steeper, right? I mean, the shear is low of the
yes.
lower branch, but could the opposite situation happen? I mean,
do you mean do you mean can you have a low shear branch that has a lower viscosity than the high shear branch, I guess?
Yeah.
I mean, that's tricky to imagine and then have bands in this direction because you would need to have a low slope and then a high slope, and then because it has lower slope, it would be over here rather than over here. But actually this example, I mean, you can get transitions to states. You could imagine having a constitutive curve that wraps around and looks like this. I don't actually know of any examples where that happens, but you could imagine that, in which case the branch that you start with would then give way to a branch that's less viscous over here. But I actually don't know any cases where that happens.
Okay.
Hello.
Hello.
I have a question about one of your earlier slides when you mentioned the example of the viscoelastic turbulence, and we had talked about 2D turbulence and the active pneumatic structure earlier. I was wondering what the range of Reynolds numbers at which this happens, and whether the dynamics of this transition to turbulence follow what was talked about in Professor Goldenfeld's lectures last week, where this happens at intermediate Reynolds numbers.
Yeah, so I have to apologise, I wasn't in those lectures, but this viscoelastic turbulence that I'm thinking about here is actually notionally, of course, in any real experimental systems, the Reynolds number is never zero because it's always a non-zero fluid viscosity and always a non-zero fluid density. And when you combine those in the appropriate non-dimensional way, you never get zero. But this was argued to be essentially low Reynolds or quote zero Reynolds number turbulence, in the sense that the Reynolds numbers here, now I don't recall exactly, it's a long time since I've read those papers, but it may even be as low as 10 to the minus 2, something like that. So as I said, I think previously, this particular case here, where you have very highly entangled long chain-like molecules, this is something not that isn't driven by an increase in the Reynolds number. It's driven by instead an increase in what's called the Weisenberg number, which is this product of the relaxation time and the shear rate of the system. On the other hand, there is a whole map that's been mapped out. So there's an article actually just about to come out on instabilities, probably, yes, in fact, it's on the archive. There was a workshop at Princeton a year or two ago, and there are about 20 or so of us as authors who've written this overview of instabilities in complex fluids. I wasn't an author of this part of it, but there's been a lot mapping out turbulence in the plane of, now imagine, I'm just using my cursor on this slide, not pointing to any features on this slide, but imagine you have an axis here, which is the Reynolds number, and an axis here, which is the Weisenberg number. The inertial turbulence would be at a high Reynolds number here, but zero Weisenberg number. This kind of turbulence I've just talked about is at a high Weisenberg number and zero Reynolds number. Now, you do actually get a whole zoo of instabilities in this plane here, which I haven't worked on directly myself, but there's stuff like, for example, so someone called Mike Graham at Wisconsin has done a lot of work on how you can take Reynolds turbulence at high Reynolds number, and you can add a small amount of polymers, and you can actually relaminarize that turbulence by adding polymers. So that's an example where adding some polymer actually makes the system less turbulent. Whereas this turbulence that I'm thinking about here is turbulence that arises only precisely because you have polymers at a high Weisenberg number. Yeah.
Are there any other questions? Okay, let's thank Suzanne for her lecture.